Now we get into solving the problems modeled with rational equations. So rational equations are composed of a bunch of ratios, the quotient of two numbers or quantities. They can be variables, they can be algebraic or numerical. A proportion is a mathematical statement that sets two of those ratios equal to each other. So we're going to have a lot of proportions and using proportions when we are dealing with these real-world scenarios because we're often comparing two quantities. When we're comparing two quantities, we're going to have a proportion. Rates are just ratios that have different variables or units when we are comparing two things. Common rates that we'll see are things like miles per hour or liters per minute. When we have different units like distance and time or volume and time, so different units will use rates. And there's a couple different common types of rational equation word problems that we'll see, as well as a few other examples that we'll go through. And they all follow a very similar structure, but you have to think very carefully about the rational expression that models each part of the scenario and build an equation to model around it. So in our first problem, we have a certain number is subtracted from a numerator and added to the denominator of a given fraction. And so we can actually represent that to start. We have something that we don't know being subtracted and added to this fraction. Well, the thing that we don't know is our variable, so we can use x and any other variable we want. But how this is structured is that we're taking this fraction, 9 over 19, and we're subtracting this unknown number from the numerator, but we're adding the unknown number to the denominator. And so now we have this rational expression that models this first sentence here. This first sentence is modeled by this rational expression. Then it says that the new fraction is equivalent to 1/3. It equals 1/3. Well, we have one ratio set equal to another. Now we have a proportion. And we solve a proportion just like we would any rational equation. We want to multiply both sides of the equation by the LCD, which is the product of our two denominators. So we can go ahead now and we can multiply. Let's change our color up here. We multiply both sides of our equation by 19 plus x and 3, 19 plus x and 3. 19 plus x is going to eliminate from the left side, 3 is going to eliminate from the right side, leaving us with 3 times 9 minus x equals 1 times 19 plus x. So we apply our distributive to simplify. We're left with 27 minus 3x equals 19 plus x. Now that our fractions are cleared, we'll solve. We can add to group our like terms. Subtract our constant. And then we can divide by 4 to get the value of our solution. Oftentimes we'll see proportions as comparisons between part and whole. So in the United States, 7 out of every 20 homes built in 1990 are heated by electricity. So this right here is a ratio that is representing a part to whole relationship. Part to whole. So the part is 7 while the whole is 20. We have this ratio 7 out of 20. At this rate, so we have that comparison, that part to whole comparison, how many homes in a community of 16,000 would be predicted to have heat that's powered by electricity? And so we have a equivalent rate in forming a proportion. Well, the part is the thing we don't know, but this represents a total or a whole amount. And so the denominator becomes our 36,000, and we're left with the unknown of x. So simple multiplication here. We'll multiply by the least common denominator. 20 is actually a factor of 3,600, so we can multiply both sides by 3,600. Or sorry, 36,000. Cancels on the right. We're left with x equals 36,000 times 7 over 20. That will reduce, and we multiply, so we're left with 1,800 times 7, which equals 12,600. Now these next few are types of problems that we'll see a lot of. First one is we have this combined work type of problem. We have Alyssa here who can clean the house in 4 hours, and her husband can do the same job in 5 hours. And we want to figure out how much or how long it will take them if they clean together. So what happens when we combine the work is that every hour Alyssa completes a certain amount of the task, and her husband completes a different amount of the task in that same amount of time based on how fast they work. And working together, they will complete the job in a shorter amount of time. So what we're looking at is the amount of time, or more specifically, the amount of the job Alyssa can do in 1 unit of time. And that unit is usually going to be based off the problem and what unit they're using to measure time. Here we're measuring time in hours. And so we're going to think about how much of the job Alyssa can get done in 1 hour. And we're going to add it to the amount that her husband can do, again, in 1 hour. And when we combine their work, it's how much of the job is done per hour when they work together. And so that's the general structure of these combined work problems. How much is done in 1 hour plus how much is done in 1 hour equals how much is done together when they work for 1 hour. Well, if it takes Alyssa 4 hours to do the job, say it takes her 4 hours to do the job. Well, it's broken up into 4 increments. Every hour, she's completing 1/4 of the job. So after 1 hour of work, Alyssa has cleaned 1/4 of the house. Now her husband, it takes him 5 hours to do the job. And so his is broken up into 5 increments. But again, within that same amount of time, he gets 1/5 of the job done. And so since they're working together, we can add Alyssa's 1/4 of the job to her husband's 1/5 of the job, and we can figure out how much is done when they work together. 1 out of some unknown amount. And so this is this very basic structure that's going to be repeated a lot when we're looking at combined work problems. So within 1 hour, Alyssa can do 1/4. Within 1 hour, John can do 1/5. And then we can find how much they get done together. And X represents the amount of time to do the whole job. And that's the beauty of this setup. Once we solve for X, we know the amount of time. So we'll multiply both sides of our equation by our least common denominator. 4, 5, and X gives us a LCD of 20X. 20X and 20X. So we simplify, we're left with 5X plus 4X equals 20. And then we get 9X equals 20, X equals 20 over 9, which is approximately 2.2. And so if we go back and look at this structure again, in 1 hour, they complete 2.2, 1 out of almost a little bit more than half of the job. So in 1 hour, they get that amount done. So it takes them a little less than 1/2 of the job. It takes them 2.2 hours to finish. Well, since their movie on TV starts in 2 hours, unfortunately, they're not going to finish in time. Here we're looking at comparing rates. Comparing rates is also going to show up a lot. So this person, Keith, it takes him 1.5 times as long to go 72 miles upstream in his boat as it does to return. So they're going the same distance. The boat cruises at 30 miles per hour in still water. What is the speed of the current? A lot of times thinking about what the question's solving for will really help in identifying the variable and what we're using in our expressions. The speed of the current is going to be our variable x. I'm going to use actually c for current. C equals the current's speed. Now, since we're looking at rate and time and distance, we have a formula for that. Distance equals rate times time. Now, depending on what we're comparing, we can often rewrite this equation in different ways. We can isolate t by dividing with r, and we get time equals distance and rate. Or we can divide by t, and we get rate equals distance divided by time. And so we can use these relationships to write a rational expression based on the information we're given. Well, what we're given, more specifically, we're given this time comparison. So that means we're comparing time to go upstream versus time to go downstream. Now, time to go upstream, time upstream is equal to 1.5 times time going downstream. So we have this basic structure, but I don't know how long it takes him to go upstream. I don't know how long it takes him to go downstream, but we have this comparison of time. And since we have this comparison of time, we can treat time as being equal and replacing it with distance and rate. So if we replace time upstream with distance upstream over rate upstream, and we set it equal to 1.5 or 1.5 times distance downstream divided by rate downstream, now we have some more information that we can substitute into our equation and solve. So Keith McQueen takes 1.5 times as long to go 72 miles upstream, so the distance upstream is 72 miles, and he goes the same distance downstream. So those two values are going to be the same. Same upstream and downstream. Now we still have the 1.5 being multiplied. Well, now we need to figure out the rate going upstream and the rate going downstream. Well, we're told that the boat is 30 miles per hour in still water. So we're going to start with that. The boat moves at 30 miles per hour. But we have to think about what going upstream and downstream does. When we're going upstream, we're fighting against the current. So the current's going to slow us down. So when we're going upstream, it's going to be the speed of the boat minus whatever the current is doing to slow us down, however fast the current is. When we're going downstream, the current speeds us up. We're going faster. So it's the speed of the boat plus however much the current is pushing against us or with us to make us go faster. And now we have our rational equation in one variable. We can go ahead and solve. So now that we have everything, we can multiply by our least common denominator. We can actually distribute this 1.5 first into the numerator and simplify that, and then multiply by our LCD. 72 over 30 minus c equals 108, 30 plus c, and then we can multiply by our least common denominator, which is going to be the product of both of these. So 30 plus c, 30 minus c, 30 plus c, 30 minus c, We cancel the 30 plus c and the 30 minus c. So we have 30 plus c times 72, 108 times 30 minus c. We'll go ahead and distribute. Combine like terms. We'll add and subtract to both sides. And then divide by 180. And we get the speed of the current as 6 miles per hour. So when we're going upstream, the current is slowing us down by 6 miles an hour. When we're going downstream, the current is speeding us up by 6 miles per hour. Here we have another rate problem. The speed of the river's current is 5 miles per hour. A boat travels 20 miles downstream in the same amount of time that it travels 10 miles upstream. So just like we did before, we're comparing time upstream versus time downstream. And the time upstream and downstream are exactly the same. Up equals time down. Well, since the time is equal, then what we're really doing is comparing the distance going up divided by the rate going up has to be equal to the distance going down divided by its rate going down. Remember, going upstream, we're going to go slower, and downstream, we're going to go faster. So the distance upstream is 20 miles. Or I'm sorry, distance downstream is 20 miles. So our distance down is 20, and our distance up is 10. We want to find the speed of the boat. That's our variable. So B equals speed of boat. You could use X or any other variable, S for speed, R for rate. The speed of the boat is B. So when we're going downstream, the current is slowing us down by 5 miles per hour. Sorry, when we're going upstream, the current is slowing us down. When we're going downstream, the current is speeding us up by 5 miles per hour. So we're going to have B minus 5 to go upstream, B plus 5 to go downstream. Then we multiply by our LCD. We simplify. We're going to use our addition property and divide. So the speed of the boat is 15 miles